Okay, good morning, everyone. We have 45 people and let us start 2 minutes late. So we have many things to do today, and I recall your exam 1 is done, but still we have many things to do. I want to show you something. As I promised, after each exam, I show my screen now. After each exam, I show some kind of diagram. So please take a look here. Look at my screen. So what you will see here is exam 1 score plotted versus average scores for homework 1-3. Again, there are maybe technical bugs here because some people did not take exam, some people did not write homeworks. So by what you generally see here, I recall each of you corresponds to one marker at this diagram. This is one student. Exam versus average homework. And I do suggest, and you will see it from here, that most of the scores go along this big diagonal, or at least along it. So you will see that really what was the best hint how to write exam well? Please do your homework and do it yourself. Okay? Well, you may see some people manage to write exam with bad homeworks. It's great, but it's only 1 or 2 people like this. In contrast, you may see that very few people who do well at homeworks but fail with the exams. There are some people here, and well, what might it be? It may be that you were bad of luck last exam, or it may happen it was timing question, or maybe you did not do your homework yourself. Again, it happens. In other sections, I know in other instructors, typically, well, when you have excellent homeworks but very bad exams, they give F because for the entire course because they say that it cannot happen. So it's not your homework. I never do it like this. Your homework is your homework. You deserve it. And if you copy your homework from your friends, you may see now that you penalize yourself. Homeworks cost only 10%. They will not replace your exam. Most likely you will see 80% of you, really for 80% of you, exams and homeworks more or less correlate. For some of you, actually, exams are even better. So please, I will encourage you one more time. Please continue and please do your homework. Do your homeworks yourself, and you will be okay. So today is Friday, October 9th, right? So your next exam is just in 3 weeks. Just in 3 weeks, it will be Friday. It will be October 30th. Procedure will be the same. You know how to make it. So please don't relax. It's quite soon. Now you have your homework number 4, which is posted, which is sent to you. And again, I apologize for all technical troubles we have with the campus. Now your scores and your homework should be seen. So your exam homework 4 is posted. It will be due next Friday in 1 week. And the help sessions will be Wednesday and Thursday next week, 2 business days before as usual. So please take this opportunity. Attend help sessions. It's very convenient. Sometimes it's much more convenient than the morning before your due date. You realize you need to ask questions. Please come and ask. Now, then and again, I recall chapter 4 is not very difficult. So if you're still struggling with chapter 3, it's really time to pick it up and to proceed. After this, it will be homework number 5. It will be chapter 5. Which is not so easy. We will talk about open systems, and after this, we will have your exam. Your midterm reports are due Tuesday, and this weekend I will post it. Again, don't take midterms like something official. It's not. It does not indicate any final score, but it's a good hint because most likely your midterm score, it will really correlate with your final score. Your midterm score will be based on your exam 1. With maybe some small correlations with homework. So for instance, if you really have drastic change between homeworks and exam, I may correlate it. But basically your exam score is your midterm score and you will see it posted. Okay, does it make sense? I believe so. Now, I come back to my slides. You see my slides now, and I recall what we are doing here. So last time we discussed all our objectives. So basically, we talk about closed system. Typically, it's something like this, like a piston cylinder assembly, which can be with constant pressure, constant volume, whatever it is. And we discuss processes. Unlike chapter 3, now we talk about processes. We will never have one state. We will have several states. So we have so-called quasi-equilibrium process between state 1 and state 2, for instance, and your task will be to identify both states and identify work done here, heat transfer, change in energy, and so on. So please, again, I repeat something so many times because I want you to remember. So what you will have some kind of equation of the process here. And this equation should be known, should be considered. Now, you will have first law, which is energy balance. I considered it last time. And what is boundary work? What is work here? Q and W, it's heat transfer and work transfer in this process. Please remember that work is not necessarily boundary work. It's okay if you most likely we deal with boundary work in this class, but there may be other forms of energy, like electric energy, like stirring, like mixing. It may be something happens with closed chamber with mixing. So please realize it. So these items can be different. And potentially you may have one more source, which is work other, how I say it here. Now you have this equation of the process. And also, you know that your boundary work, only boundary work, it's nothing but integral PDV, that's the surface area in this diagram. That's what it is. So in fact, what you're doing all the time, you are solving this set of equations. But now, very often it will be simplified because you don't have some terms here. Well, you may have more terms here, right? You may have more processes. So it may be not one process, you may have many of them. Then you should be able to do what? You should be able to do the system for each particular process. For this one, and one. And when you integrate it over the cycle, you will come to what? That energy does not change over the cycle, and you have that heat over the cycle is equal to work over the cycle. Q net is equal to W net. They both can be positive, they both can be negative, but they are not zero. And we are lucky because of this. We are lucky that there is no conservation of work and heat because they are additive and they are transformable. Energy cannot be destroyed or generated, but it goes from one state to another. So heat and work, heat can be converted into work and work into heat. And why? Because both heat and work are not the function of state. They are function of the process. Remember, they're not property. So that's why when we start with one point and after a cycle go back to the same point, still it will be zero for a cycle if it's a property, but it will be not zero for Q and W. Remember this. So that it is what you have. Yeah, oftentimes your energy will be just internal energy. So instead of E, delta E, it will be delta U. And then we discussed last lecture, remember for a while, that what kind of equations POV you want to see. And most likely we deal with what? We deal with polytropic processes. So that is polytropic. So remember what is polytropic? It will be equation like this, PV to the power n is constant, or like this, P1, V1 to the power n is equal to P2, V2 to the power n. So you know this equation and you will be solving. So again, look at this picture. Most likely you have this equation. You know state 1, for instance, you know P1 and V1, and you know, for instance, V2. And N is a polytropic index, which is maybe known. So then, will you be able to find P2? If you know one state, will you be able to identify second state? I believe so. You identify it from this equation. Or vice versa, you know state 2, and you will be able to identify state 1 from here. That's what you do in your homework number 4, number 5. For instance, in homework number 6 is different. In homework number 6, you need to find N. Will you be able to do it? Imagine you know P1, V1, P2, V2. Will you be able to find N from here? Right? From it's logarithmic equation. You will write, it's mathematical question. It will be logarithm of pressure divided by logarithm divided by of volumes, right? Recall mathematics. So that's what you typically have. You know P1, V1, you will find P2 and V2. You will substitute it here. You will find boundary work here, and then you will be able to find Q, U, and something like this. That is your task. Does it make sense? I believe so. Now, why polytropic processes? We considered last time. One thing, because polytropic equation of this form is easy to integrate. Second, because typical process that we have in practice are polytropic indeed. So remember, we discussed it for a while. So basically that n here is some constant, and depending what n is, you will get some process that you know. For instance, if n is equal to 0, it's isobaric process, pressure is constant. If n is equal to plus or minus infinity, it's for ideal gas, it will be isothermal. If it will be isochoric. If n tends to infinity, it will be isochoric. If n is equal to 1, for ideal gas, we have isothermal process. And you have this table. We didn't touch adiabatic processes yet. We will talk about this maybe on Monday. But you may realize that all iso processes we deal with, isobaric, isochoric, isothermal, adiabatic, isentropic later, they are actually polytropic. That's why it's so convenient to consider polytropic process. It describes reality. And second, why it's convenient, because it gives you nice formulas. You are able to integrate on PV diagram, you're able to make integration and get it. Right? So remember this formulas I recall we discussed last time. So generally speaking, for any n except for 1, your boundary work will be this one, this formula. You see it, right? So basically, you know the formula, you can use it. But why we derived it? Because I recall that you should not use this formula all the time. For instance, if your n is equal to 1, it gives you singularity. So for n is equal to 1, you should use this formula. You should use PV logarithm and volumes ratio. Okay, otherwise, this formula is for arbitrary n. Even for such particular cases like isochoric or isobaric, it works. Because if you take n is equal to 0, you will come to formula which is selected by gray here, right? It will be isobaric process. If n tends to infinity, this formula give you 0. So as it should be for isochoric process. What is isochoric on PV diagram? It's vertical line, and there is no area on the vertical line, so it's 0. Remember, if you have rigid tank, boundary work is 0, dV is 0, boundary does not move, boundary cannot produce the work. Does it make sense? Again, remember our classical convention here that work is positive for expansion if it's done by a system. Work is negative for compression if it's done on the system, active and passive voice. So basically, always remember, if you have expansions, they should be positive. If you have compressions, they should be negative. If you misled it, if you get something different, that something is wrong. Right? We discussed it last time. And basically also we considered the example. I spent again time on this because that is some basics that I don't want you to miss. This is something that you need to remember. This is your homework, but I want you to show something else. I remember last time we considered a couple of examples from your textbook. And we discussed that boundary work is 0 if you have isochoric process. Here is, you may see my screen. This is PV diagram. What is isochoric process? It's like this. Whatever it is, compression or expansion, here it's actually expansion. I mean, here it's pressure drop and pressure jump. So basically, what does it mean here? As soon as you don't have change in volume, there is no surface area under this line, and boundary work will be 0. For other process, we consider what happens if you have isothermal process, and you may realize here that it is, right? And basically, last time we considered the example for ideal gas. You can look again, it's example for a new textbook. So how we are solving the problem? You use here state 1, which was given pressure and given temperature, and you identify state 2, and based on this, you take your integration, and that's what you calculate, right? And you find this value. And you got that boundary work will be negative because it's compression, right? It's compression, you go from state 1 to state 2, so this surface area is positive, but work is negative. Work is equal to minus this surface area. Any question about this? Well, in general case, you consider basic equation, it will be like this. So basically, you don't know n. So basically, you should be able to solve this equation properly, and you should be able to solve it, identify another state from 1, and consider. And we consider these examples, right? So let me see if we can consider any more. I will come to this example a little bit later. Okay, does it make sense? So basically that it is. If you look at your homework, here is your homework. So please just Let's look at it together. And basically, here are your equations. Let's see what we have here. It's stated here that let's look, for instance, in problem number 6. Let's look together. What is stated here? You have piston cylinder device which has 5 kilograms of air initially at 5 megapascals and 32 degrees Celsius. Then air is expanded isothermally to 400 kilopascal, and then compressed polytropically to the initial pressure. And finally, it's compressed to the initial state. You will need to determine all these items like boundary work and so on. So what you should do here? I request you to remember the following. In all these problems like this, in all problems like this, you identify states one by one, okay? You will identify states by one by one. So what do you know here? Do you know states? So you have air at 2 megapascals and this 320 degrees Celsius. Will you be able to identify the state? Yes. Now, what is stated there? Then air expands isothermally. So it's isothermal expression for ideal gas to this value. Will you be able to identify state 2? Okay, yes. Then what happens then? It's compressed polytropically with polytropic exponent, this one. Do you know what, and then it goes to initial pressure. So now you can write down a polytropic equation. What is polytropic equation? PV to the power n is constant. So you will have P3V3 to the power n. It will be P4V4 to the power n, right? Do you know n? You know n. It's 1.2, right? Do you know initial and final pressure? Do you know initial and final volume? Final volume you will find from here. So will you be able to calculate boundary work from here? I believe so. So please try, and you realize that it's not only one equation here. So that is something that I showed you on this picture. So here it's here, right? So basically that's what you see on the right hand side. You should write down this equation for each process. Yeah, I don't say it's like this. It's not like this. It will be something different, but you should be able to find state 1, state 2, state 3, and so on. And then you will be able to write down this equation in total. Does it make sense? And only one of this equation will be linearly polytropic with polytropic coefficient n, and you will consider. Now, again, I recall, if you know you identified state 1 based on your tables or whatever, you still know nothing about state 2, nothing about state 3. All the time you solve chapter 3, you solve this problem from chapter 3 from the very beginning, right? It's a must. Don't forget about this, because this is a classical mistake when you extend your knowledge from one state to another, which can be wrong. Okay? Now, so that's what we are doing. Now, another example from your homework, for instance. Look at problem number 5. What is stated here? We have piston cylinder device which initially contains 0.2 meter cube of nitrogen at this given 175 kilopascals and 120 degrees Celsius. Okay. Do you know state 1 here? So you know you have nitrogen, you have this pressure and temperature. So do you know the state? Do you know P1 and T1 will be able to find V and V1? Yes, you know. Excellent. Now, what do you know else? The nitrogen is now expanded polytropically to the state of 120 kilopascals and this one. So now you know you will have this value and you have this temperature. Okay. So do you know state 2 now? Well, you know pressure and temperature. Nitrogen is ideal gas. Will you be able to find specific volume for this state as well? I believe so. And total volume, because actually you can find the mass if you need. Now, what is the point? So you know that the process, you know P1, V1, and P2, V2. But what you don't know here, what you don't know? You don't know polytropic exponent. You don't know n. Okay? Tell me, please, will you be able to find n if you know all other terms? Here is your equation, correct? If you look on big screen. Here is your equation. So if I know P1 and V1, and I know P2 and V2, will we be able to find them? Yes. So from here, you should be able to find N. It's not typical because typically you know N and you don't know other items, but here you should be able to find. Now, it's stated, please find the mass and volume of nitrogen at the initial state. How you find mass? How you find mass? Well, what is mass by definition? It will be the density by volume, it will be rho V, or it will be V divided by specific volume. Do you know your volume at the initial state? Yes, you know. Do you know your specific volume at this given pressure and temperature? Do you know it? So will you be able to find it? You will be able to find specific volume? Yes, exactly. You know ideal gas law. Exactly. Yes, exactly. So and what? Will you know mass and volume as initial state? I believe so. Now, what will be final state? Will mass change at the final state? It's closed system, so mass will be the same. But what about volume? Will volume be the same? No, volume will not be the same because it's stated here that you have polytropic expansion. So your volume expanded. You will have new specific volume, new total volume, right? And that's okay. Mass will be the same because you change specific volumes. Density will change. Does it make sense for you? And will you be able to find boundary work? I believe so. Why? Because, well, what is boundary work? It's just integral PDV, which you'll be able to integrate. You have polytropic process, and we discussed it. So here it is, right? You already know how to deal with it. Do you know the formula? Which formula will you use? You will use that formula? So what is your P1, V1, P2, V2? Will you know it? Yes. Will you know N? You will find it, right? So that it is. Again, I'm not solving problem here. I give you hints. It's your homework. You should solve your problem yourself. Then you'll be good at your exam. But that's what your typical strategy, what you consider. Identify both states and then calculate boundary work and write down first law. Does it make sense? Any question now? Now, I want to focus specifically, before we proceed to heat capacities, I want to focus specifically on isobaric process. And remember, it's important to remember, so generally speaking, for isobaric process, what you will have from this equation? You will have that boundary work, it's P delta V, right? It's understandable, right? It comes from here. And basically, if you look even in your example, in your textbook, in simple example in your textbook, like I considered example 2, you will realize that for isobaric process, what is this? This surface area, it will be integral, so it will be P delta V, correct? That's what you have, P delta V. But I want to focus on something else. I want to focus on enthalpy and on heat transfer in that case, because remember what is enthalpy? We introduced enthalpy like U plus PV, and I told you that enthalpy will play a crucial role in this course, so you should be very flexible with it. Remember, enthalpy does not exist in reality, but it's very convenient parameters which helps you to solve the problem. It's like adjustable gross income. Remember, energy exists. Enthalpy is just a combination U plus PV. Now I recall what I did in chapter 3 because I want you to consider it seriously and solve some problems. So what we have? If we write down first law of thermodynamics, I recall it looks like this in differential form, right? du is dq. Well, this is heat, this is work. I write delta here because they're not exact differential, they're a function of the process. So if what happens like this? It's my dq minus pdv, correct? So if I have isochoric process, that is, if my volume is constant, what does it mean? It means that I don't have the storm. my boundary work will be 0, and I have the delta U is equal to Q. So if you ask me what is heat transfer in isochoric process, it's very simple to answer. It will be this. Correct? Does it make sense for you? So internal energy, it's a good item to deal with. It's a good function to deal with for isochoric process. But what about isobaric process? In isobaric, will you have exactly the same equation in isobaric process? No. Why not? Because for isobaric process, this term is not cancelled. You have boundary work. True? True. But we are still lucky a little bit. Because for isobaric process, still it's some simplification. So you don't need to take integral. You can do something simple. And for this reason, remember what we do. We introduce enthalpy. Because remember what is enthalpy? Is U plus PV. So if I write this equation, what I have here? I have here that Q will be what? It will be delta U plus P delta V plus work. Okay? And what I write here is my general form of equation. So if my pressure is constant, I will take it out of here. I will write M delta U plus this, and I will come to this equation. Does it make sense? So that is my Q. And in your home, and that is how you may calculate. Okay, that is your expression. And if I stop at this point and I go to your homework again, what I will see here? I will see, look here, for instance, it's homework problem number 3, for instance. It's stated, 4, let's do 4. A free piston cylinder assembly initially contains 7 kilograms of saturated liquid water at 300 kilopascals. So state 1 is saturated H2O at 300 kilopascals. So do you know the state? Do you know everything in state 1? If it's saturated liquid. So everything will be VF, UF, GF, HF, right? All these parameters. You know specific volume, everything we need. And then it's stated that the cylinder is gradually heated until eventually liquid has vaporized saturated vapor. So as a final state, you have saturated vapor only, correct? So do you know second state? Your second state will be saturated vapor. At which pressure? It will be exactly the same pressure. It will be 300 kilopascals. So you have the same pressure, you know all final parameters. Okay? And then it states, they ask you, what is the volume of water at the initial and final state? Right? How you'll find it? How to find the volume? Will you be able to find specific volume at the initial and final state? I believe so. Will you be able to find total volume if we multiply by mass? I believe so. Will you be able to find boundary work and heat transfer? And now you may say, okay, boundary work will be P delta V, heat transfer will be exactly what we discussed here, right? But I recall you something, that's why we introduce enthalpy. So that's how you may solve it. So if you solve this problem like this, it will be okay. It will be okay. Do you know U1, V1, P, yes? Do you know U2, V2? Yes. So basically, if you calculate everything like this, you will come to correct answer. And I don't mind if you do it. And boundary work will be what? It will be this P, V2 minus V1. But I recall, for isobaric process, it is enthalpy, which is good parameter to deal with. Remember enthalpy? It's U plus PV. This is total enthalpy. Specific enthalpy, it's U plus P small v. Yeah, one more comment from exam. Many people did mistakes. So please remember the difference. Between specific, it's per unit mass. It's small character. If I ask you total enthalpy, I ask you multiply it by mass. If I ask you for total internal energy, it's capital character. It's this one. Please remember the difference. Many people confuse it. Now, if it's like this, I know that what my DH is du plus d of PV, and it will be, I can split it like this, dq minus pdv, and what is d of PV? It's like this. So basically here what I do, I switch between conjugative parameters, and my DH becomes dq plus vdp. Look at this equation and look at my first equation. What is the difference? What is the difference? The difference is quite simple. Here I got rid of this term if I have constant volume. If I'm here, if I have constant volume, will it help me? Not much. But if I have constant pressure, I will get rid of this term. And what I will have? I will simply have that if I have constant pressure, that my Q is nothing but delta H. Do you agree with me? Delta H. So now, and the same I wrote here. So you may realize that instead of playing around U, P, and V, instead of playing around with specific volume and specific internal energy, I can play around with enthalpy only. Okay? I will have the delta H is nothing but mH2 minus H1. Is it much simpler? Can you take your enthalpy in this state and initial state and final state and calculate? So that's what you have. So what you should recall from here, for isochoric process, Q is equal to delta U, period. Q is equal to delta U. Boundary work is 0. For isobaric process, Q is equal to delta H, period. And it's simpler to deal with. So instead of having 4 terms, I will have just this. Do you understand? That's how you calculate. So what will be your boundary work? It will be P, V2 minus V1, VFG. What will be heat transfer? It will be this M, H2 minus H1. And now in our particular case, come back to the problem we considered. Remember, at state 1, we have saturated vapor. And at state 2, we have, at state 1, we have saturated liquid. At state 2, we have saturated vapor. So in our case, what will be H1 and H2? What will be it? Please answer. Exactly. It will be Hg and Hf, right? And what will be their difference? It will be HFG, correct? So in fact, in my particular case, it will be nothing than what? Here you will have simply HFG. Do you agree? So instead of playing around with 4 terms, I will have only 1 term, HFG, which I can take from the table. Recall this, at this point, let me open again, for instance, slides that we deal for chapter 3. For chapter 3, part 2, right? And remember, we talk when we consider examples. I think it was here, right? Yes, here it is. Remember, well, that is the example that we consider. You may see it on the screen. Remember? So what we have here? Here is that was exactly examples from your homework number, right? But pressure is different. Now pressure is not 100 kilopascals, but pressure is 300 kilopascals. But otherwise it's the same. So what we have at the very beginning? This is saturated liquid. This is saturated vapor. Okay. So what will be work done if you can consider it like this? It's exactly your examples from your homework. What is boundary work then? It will be this, right? Do you agree? So boundary work will be what? Here. It will be what? It will be P delta V. Correct? Do you understand? Do you agree with me? But also what it will be in our case? Instead of V, you can write it like it will be what? It will be P M and what? What will be delta V? It will be V2 minus V1. Correct? Do you agree? What is V2 and V1 in our case? What is V2 and V1? It will be VG and VF. Do you agree? Everybody understands this? Everybody understand why mass is out of brackets? Because mass is constant because of specific values we talk about. And what is Vg minus Vf? It will be actually nothing but P M. And here I will write V. And here I can write what we call F G. Do you understand? Do you understand this? Do you agree with me? Good. Excellent. And some of you replied earlier than me. Now, if I talk about heat transfer here, what will be heat transfer? Let me clean everything here. So we decide that heat transfer will be what? We decided that heat transfer will be Q. It will be what? It will be delta H. It will be what? It will be M H2 minus H1. What is H2 and H1 in our particular case? In our particular case, they are Hg and HF. So here I will have nothing that M H sorry. H F G. Do you agree? So why we talk about this? How many parameters you should take from your table for this equation to solve this? How many items should you need from your table? Just one item. HFG is already in your table, remember? Remember? But otherwise, if I don't give this formula to you, what you will do? You will use UF, UG, VF, VG all together, which will be a little bit more complicated. Do you agree? I believe so. Now, when you are here, you go to your table and you see VF, VG, and you can take all VF and VG here. So here you have in your table HFG directly. Is it helpful? I believe so. I believe this is helpful. And the same story here. So if you look at the screen, what you will see here. Again, you can use this formula if you want, this blue formula. You can use it. You can use it like this. And here you will come to exactly, if you consider here, you will come to exactly the same answer. What will be V1 and V2 here in all cases? It will be VF, VG, UF, UG. But altogether, it can be easily combined to this one, which we just calculated. Does it make sense for you? And again, when it happens only if you have isobaric process. If it's not isobaric, if pressure is constant, if pressure is not constant, what I'm talking about will be wrong. Do you agree with me? It will be wrong, and you cannot use it. Please understand, it will be wrong. If you have isochoric process, what I'm talking here, it will be okay, but it will be useless. It will be useless because you don't need to calculate boundary work at all. Ask me something. Does it make sense? And again, I recall when you write first law, like you did it here, like you write first law. Here, you should realize that generally speaking, you may have boundary work here, right? Generally speaking, you have boundary work plus something else, like electric work. And you have very good example in your textbook, and we discuss it, and now let me discuss it again. It's a good example in your textbook. Well, before I go to textbook, so if I go back to your homework problem, here it is. So do you know now how to solve problem number 5? Everything is clear? Everything is quite simple now? And I mean problem number 4, everything is clear now?
So did you say for an isothermal process, Q equals M delta H, that doesn't apply? Is that what you said?
Yes, it does not apply.
Why?
Why it should, let me ask you vice versa. Why should it apply? Why should it apply?
Temperature is constant.
What we derived here was when pressure is constant. Do you agree that what I'm talking about here, everything I talk here, it's when pressure is constant. If pressure is not constant, everything will be different. Do you agree?
Yeah.
Okay, that's why. For the thermal process, you consider just a very general equation, because now you need to take integral PdV instead of taking P delta V. Okay?
Yep, thanks.
Okay, well, yeah, welcome. So basically here, now if you talk about your homework problem number 4, does it make sense how to solve it now? Here, you are lucky. When you read about free piston cylinder assembly, you are lucky to use the simplification. And basically, all these equations can be solved. In general case, if you have different pressures, like you see here in problem number 3, you solve your equation like it is. That's a general form. And now also you should be able to get your data, your knowledge from the text. If it's stated you have rigid tank, it means that volume is constant. If it's stated you have free piston cylinder system, it means that pressure is constant. If you stated it's isothermal, temperature is constant. If it's stated it's adiabatic, Q is 0. Based on this, you may get some knowledge, some data that you can use. And in your homework, or in the textbook, now, so in your homework now, I believe you know how to solve problems number 4, 5, 6. It should be more or less okay for you. Please, you have this weekend ahead. Please do it. And if you have questions, bring it on Monday, because it's really important. Again, it's something basic, but something simple. When you get it, it will be easy. If you don't get, you stuck. So please do it. Now, and in fact, we discuss this problem. So again, only if you constant pressure, I can to this topic, we come to this. So you have these relations between delta U and delta H. You have this formula. You may ask, why don't you use it for isothermal process? Answer is simple, because we derived it only for isobaric. Again, what you see here in the formulas, it's exactly what we talk about. But what we talk here, that imagine that instead, in addition to boundary work, you may have something else. You may have extra work. So what you see here, it's exactly what I discussed at first slide. So basically, remember here we are. So basically, you have this term and you have energy change. Correct? I have W is equal to boundary work plus other work. Then I should account for it, and that's what I have here. And the left-hand side you see here, what I write. Q minus W is delta U. It's nothing that first law. As often you neglect kinetic and potential energy. But now we realize that what is W here? Your W here is what? Your W here is nothing but it's a combination of this. Correct? So you express it as follows: other plus the boundary work. What is your boundary work for isobaric process? Your boundary work will be here, correct? That's how you arrive. So eventually you come to this formula that Q minus this work, it can be electric work, it can be anything, minus this is give you delta U. And now you see what you see here. You have this equation, what I wrote here. I expressed, I combine together U, and do you agree that this equation can be rewritten like this? Do you agree? It's the same, right? I just change parameter, change orders of terms. And do you agree that this, what is this one? It's enthalpy. What is this one? It's enthalpy. Correct? So now you come to this formula that Q will be what? It will be, let's say, W other, let's say electric work. plus what? Plus delta H. Is it similar to what we discussed before? Exactly. Now you have work done by other source, like electric work. If there is no other work like this, if there is no other storm, is exactly like we discussed before, Q is delta H, but now you have this storm. And there is good example, I discussed it last time, but let me recall it. So imagine you have something like piston cylinder assembly here. You have water, you have its mass is 25 grams, and you have pressure, which is 300 kilopascals, 3 atmospheres. So what happened here? At the very beginning, you have saturated vapor. Okay, it's state 1. Now, what happened next? Next, you put here electric heater, and you will heat it. So you do electrical work. What is electrical work? Electrical power, it will be voltage by current by time, right? And it's stated what happens here, that this, when you do it, electrical work will happen here. You will boil your system. So instead of your saturated vapor, you will have superheated vapor. And it's 3 piston cylinder. So piston will go up, your volume will increase, but on the other hand, some heat will transfer outside, and you know what heat will be transferred outside. So the question is, please calculate what will be heat transfer here and what will be work done here. Just identify. So will you be able to identify state 2 and state 1 from here? What you should do? First of all, you go like this. You have constant pressure. So basically, what will be boundary work here? I put it wrong, it will be vertical, it should be vertical, right? This is what your boundary work is. P delta V, correct? What will be heat transfer? Now you may see here. But what will be other work here? That will be your voltage multiplied by current multiplied by time. That's what you should be able to solve. Does it make sense? So now, in addition to boundary work, you have this other work term. Do you agree with me? Let's consider this on this. Let's consider this on the screen. So basically, here is the example from your textbook. Here it is. You may read the text again. You have this piston cylinder assembly. It's exactly the same. Initially, you have 25 grams of saturated vapor at given pressure, at constant pressure. You put this resistor heater with given current and voltage, and it works for 5 minutes to deposit electric work into a system. So what happened with your system? In your system, you will have superheated vapor. At the same time, your system will expand, correct? So eventually we'll have another volume here. And at the same time, you'll have some heat loss. So basically, that is a picture just exactly like we discussed on the slide. So what will happen with us? What will be our equations? So I don't repeat it again. Do you understand that exactly the same equations that we discussed? So what we have here, that it's our balance equation, that actually heat minus work together, it give you U2 minus U1. So basically, this is our equation, and that we come to the following, that Q minus work done by others is like this. Now, what is this again, and what is this? It's enthalpy. And what is this? It's, as we discussed, it's work done by electric setup. So that's all. Will you be able to find Q from here? You should. Here is it, right? So you will find Q, and whatever you need to find from here, you will find. Do you know state 1? You have state 1. So from here, you will be able to calculate, state 1, you will be able to, enthalpy 1. And from here, you will calculate H2. And then when you know H2, you will be definitely able to calculate state 2. So in this, that it is, in this equation, so what do you know? Do you know state 1? Entirely, right? Do you know Q? Do you know work done by other setup, which is electric work? Yes. Will you be able to identify H2 from here? If you know H2, will you be able to identify small h2, which is specific enthalpy from here? If you know it, if you know h2 and p2, will be able to get temperature. So that you will have that instead of saturated vapor, you will have superheated at this condition. Does it make sense? Please ask me something. So that's the basics. That's the basics, and now you are most ready. Please go through this. If I know it's not easy, but go through this example yourself at home, and you will see that now you can solve most of the problems from this homework. The only part which is left after this is what we call heat capacity. I will do this on Monday. So heat capacities are or specific heats. It's how much heat you may consume if you proceed in some specific way. Because remember, you may imagine that if you have isobaric or isochoric or other processes, then you need different kind of heat to different kind of energy to increase your temperature by 1 degree. Like if you have isothermal process, how much energy you need to increase your temperature by 1 degree? It will be infinity, right? Because you never change it. If you have a adiabatic process, how much energy you need to change temperature by 1 degree? You need 0 because it's adiabatic. You don't have heat exchange. But for typical process like isobaric, isochoric, this is a finite values, and we will consider it. And basically, why I will talk about this on Monday, but what I want to show right away, again, come back to this formula. It's very important. If you look here, if you look at this formula, what this formula gives you, that for isochoric process, delta U is equal to Q. From here, you will see that CV, heat capacity at isochoric process, will be nothing but du over dt at constant volume. While for isobaric process, look here, the same story we say that if pressure is constant, Q is equal to delta H. So from here, I will have that my Cp will be nothing but dH over dt at constant pressure. And people use these two formulas like a definition of Cp and Cv. Why? Because U and H are properties. They are in the table. They are function of the state. So your Cp and Cv, your heat capacity, they also become properties. They become function of state. And that's something that you should realize and be careful about. Okay, I will stop at this point and I will continue on Monday. Please try to do your homework as much as you can. Be in good shape. And I believe on Monday and Wednesday, we should really finalize chapter 4. Okay? Please, any question? No, for the thermal process, Q is equal to MDH does not apply. Yeah, it does not apply. I did not say isothermic. I don't know what is isothermic. I know isothermal, isochoric, isometric. Maybe you meant isometric. Isometric, it's the same as isochoric, but it's not isometric. But it's not isothermic. Isothermal temperature is constant. Okay. Any more questions? Okay, then let me stop. I will be available in office hours. Again, today's lecture will be posted as usual. And well, again, let's try to do your homework. And I will post your midterms as well. Okay, thank you and good luck.